Hi everyone. Have you seen the stars moving? Do you know we are moving even though when we are in same place? Do you know different parts of our earth are moving in different speeds? Do you know this earth rotation creates a lot of changes? Let's see in detail in this video. If you are not subscribed this channel, please subscribe. Let's go in. Let's start with Earth. Earth is the fifth largest planet in our solar system. Being the largest of the terrestrial planets, it has the population of about 7.8 billion people. Wow. The surface area of Earth is about 510 million square kilometers. It's pretty big, right? This is our Earth. Let's draw an imaginary line around the middle of Earth. And this is equator. This equator line separates the Earth into two equal halves, northern hemisphere, the southern hemisphere, and the ends are called the poles. Earth is wider at the equator and it's narrowed down when you move from equator towards the poles. Look up at the sky. Everything in the sky seems to move towards in west as a mirror image of your eastward direction. For us, it is difficult to feel the Earth rotation, but during night we can see the stars are moving with reference to our Earth. If you see the sky using telescopic camera, you can find something like this. Do you think the stars are moving, or yourself, or both? All we know that is the sun, moon and stars are moving from east to west. Realistically, the Earth is moving from west to eastward direction, whereas the sun, stars and moon are stationary. You know the Earth is rotating. If you start watching the Earth away from the Earth, it takes 24 hours to make one complete rotation. Many of us know that every point in the Earth, it takes 24 hours to make a complete rotation with same speed. But realistically, if you are inside the Earth, the planet is bigger at the equator, so it has to move fast for one complete rotation. To find the speed of the Earth, let us divide the circumference of the Earth, that is 40,000 kilometers, divided by 24 hours. So it gives us 1670 kilometers per hour speed. Just imagine, it takes 3 times faster than the fast moving bullet train in Japan. This is the fastest bullet train in Japan that runs 430 km per hour speed. Amazing, right? Equatorial region is raised around 1670 km per hour, whereas one moves north or south in latitude from the equator, then the Earth's circumference is also reduced, and thus the speed of the Earth decreases, and thus the speed of the rotation decreases from equator towards the poles slightly. And near the poles, the planet rotates at very slower rate. Do you know that is 0.00008 kilometers per hour. It's pretty slow, right? The different speed of rotation are the reason for Coriolis effect. The Coriolis effect. So in 1835, a French mathematician, Gustave Coriolis, has identified this Coriolis effect. The main cause of the Coriolis effect is the Earth rotation. As the Earth spins in counterclockwise direction on its axis, anything flying or flowing over a long distance above its surface gets deflected. This occurs because something is moving freely above its surface. The Earth moves east under the object at a faster speed. The strength of Coriolis effect depends on velocity or speed of travel in a particular direction. It depends both the velocity of an Earth and the velocity of the object being deflected. The higher the speed or longer the distance, the stronger is the Coriolis effect. Let us see the demonstration how it works. Assume you are on a blue colored train traveling at top speed and you are passing a train that is moving a bit slower. You are seeing a goal post on the slower train. You are attempting to shoot directly to the post when you and the post are in straight line. The ball travels to the side and misses the net. Why? Let's find out. Let's think big. Let us consider the Earth as a flat rotating disc. This is center, this is point A and this is point B. Point A is twice the distance from the center as compared to point B. Let us consider for one complete rotation the point A travels this much distance and point B travels this much distance. If something travels a greater distance in a shorter amount of time, it must be going faster. Look at this merry-round table. The girl throwing a ball to the opposite person, the ball deflects rightwards. For the same case in Earth, if an object is thrown from equator towards the pole, the object deflects in rightward direction. The person sitting in the center throwing a ball, again it deflects rightward direction. Likewise, in an Earth, if an object is thrown from poles towards the equator, it gets deflect rightwards. Let me explain. I have taken few pieces of papers to explain this. Sheet A representing the base and sheet B representing a flat Earth. The center is the pole and the ends are equator. When an object is thrown from pole towards the equator, it should follow a straight path. But the object moves towards the right side instead of moving in a straight line. Here is the reason. The rotation velocity of Earth decreases when moving from equator towards the poles. At the same time, the rotation velocity of the object increases when it moves from equator towards the poles. Instantaneously, the Earth speed decreases at the same time the object velocity increases when it moves from equator towards the poles. So that is the reason the objects get deflected along the direction. In a merry-round table, if the ball is thrown from any point from A to B, it deflects rightwards, which is opposite to the direction of merry-round table. Like same way, if an object is thrown from any 2 points in an Earth, it deflects rightward direction. More the distance, more the deflection. Here, the deflection depends on the speed of an object and the speed of Earth rotation. Let's think real. Make the Earth flat. In a flat Earth, the arrows moving along the equator moves faster than the arrows moving at 45 degrees. The cloud formed at the equator has the same velocity as Earth. When the cloud moves towards the north, the speed remains same, but everything below the clouds moves slower, so the cloud moves ahead of it. A cloud forms at 45 degrees north has the same speed. When it moves towards the equator, everything under the cloud literally moves faster. The cloud falls behind it. This is the actual path when an object moves towards the equator, and this is the actual path when an object moves from equator towards poles. So this deflection is only due to Coriolis effect. This Coriolis effect creates a lot of changes in Earth. Let us see the various effects. How hurricanes are formed. A low pressure system formed at the northern hemisphere. Air around it will be sucked in. The air moves from the equator, moves faster, gets deflected towards right, and the air coming from the poles moves slower, it falls behind it. This results in air current spinning counterclockwise. That is why the hurricanes formed at northern hemisphere rotates anticlockwise. If we move towards the southern hemisphere, a low pressure system forms which sucks all the surrounding air. The air coming from the equator moves faster, deflects rightwards, and the air coming from the poles moves slower, deflects behind it. So this will create the air current moving clockwise direction. Hurricanes formed at southern hemispheres moves in clockwise direction. Back to the trains. When you're hitting an object towards a slow moving train, the objects deflect rightwards due to Coriolis effect. So this Coriolis effect have no effect on shorter distances or shorter speed. See, there are many real life examples where this Coriolis effect comes to play. Birds, missiles, rockets and aeroplanes and many more. For many interesting videos, please subscribe our channel 360 seconds. So press the bell icon. Please post your comments on the comment box. See you next video. Bye bye.